And I'll share my screen. Can you see my screen?
Yes, sir.
Good. Okay, so let's get started. So what we are going to do today is to talk about a few things about sockets that you do not know, but are kind of useful to know, and talk about something which is more an OS than networks, but networks cannot live without it. So something that we'll need in the next assignment. So let's get started. So I start with some questions. Okay. So what will happen if I make, you have seen that on the client side, think of a TCP client, you do not need a bind. What will happen if I make a bind call, TCP or UDP, anyone? Can I make a bind call? Say with similar parameters, some IP address port and so on. What do you think will happen? We normally don't do, but sometimes we do for some reason. Anyone cares to guess? First of all, will it give you an error?
No, sir.
No. Good. Okay, it won't give you an error. Okay. So what will it do? If it does not give you an error, there is only one thing it can do, right? It can bind. So we normally don't do a bind call on the client because for the server we do it because everyone needs to know the server's IP address and port. So I bind it to a particular IP address and port, and then I advertise it saying my server is running on this IP this port. Whereas the only machine that needs to know the client's address is the server. And that happens when you make the connection, it automatically goes to the server underline. Okay. So we normally don't do because we don't need, but you can make a bind call on the client. It won't give you an error. It'll do exactly what bind call does. It'll bind a particular IP address port on the client side. So that IP address and port of the client will be there. Note that every socket must have an IP address and port for communication. When you are not making the bind call on the TCP client, it is just that the system, when you try to connect, finds out that you have not made a bind call and therefore assigns one unused IP and unused port. IP is fixed, okay, for the machine, and unused port arbitrarily for that connection. Okay. Okay. What about this? A connect call on UDP socket. There is no notion of connection on UDP, right? You created the socket, the server bound it, okay? The client does not even need to bind it. The first call will assign the IP address port automatically under stream, and then you do send to, receive from, and so on. Okay. So what happens if I try to connect? If my UDP client, for example, tries to connect to the UDP server, make a connect call same as a TCP client. Will it give an error? So I know you all are busy. Okay, this is a hard semester, but all I'm trying to point out is that you should kind of start asking questions, do some, fiddling around. Nothing will harm your computer. So anyway, can I make a client call on UDP client? Come on, somebody.
No, sir, it should fail.
It should fail. Okay. Anybody else?
So no,
you agree with him?
Server can't accept.
Server can't accept that. You are saying that it don't fail on the client side, but the server cannot accept it. Okay. Okay. Nothing will happen. It won't fail. Okay. So what happens is this: when you make a connect call, okay, with a, so what is the connect call saying? Gives server IP and port. Okay. No, for UDP, no actual message goes. Okay. All it does is this: it registers inside your network stack that this socket, for now, okay, I can change it with another connect call, wants to communicate with this specific server IP port. Okay, so nothing, no message goes out to anybody. So it doesn't go to server. So there is no question of server accepting, not accepting. It won't fail. Okay, it's just register in the network stack that this socket should be used to communicate with this server IP port. Okay, why would I like to do that? How does that benefit me? So it's more a matter of convenience. Okay, remember that your receive has 4 parameters, your send has 4 parameters, but your send to and receive from has 6 parameters. What are those 2 extra parameters? The IP address port of whatever the other end that you're trying to communicate with. Okay. So if I can do a connect, and then I can just use send receive, and the system will automatically understand which socket do you want to communicate with on the other side, which IP address port. Will pick up from these registers. So you just pick up automatically in this send receive call. So you don't have to type in the thing again and again. But there's nothing permanent. In the middle of all this, you can again send a send to with a specific IP address port, and then it will go to some other IP address port, whatever you specific. So all it does when you do a connect call on UDP client, doesn't send any message out or anything. Okay, it just registers that with this socket, the user has bound, kind of not bound, bound is a bad word. Okay, it has kind of associated this server IP port. So whenever anything is sent on using this socket or received from this socket, make sure that you receive from this or go to that piece. Okay. Try this out when you have time. My last question, okay, your send call, okay, or send to, etc. Is it blocking or non-blocking? Receive and receive from, we saw is blocking. Is that a blocking call or a non-blocking call?
Non-block.
Non-blocking. Everybody agrees? Non-blocking? Anybody disagrees? By default, it's actually a blocking call. So almost never will you see it block in your, what you are doing right now. Okay. Why would a send call block? Okay. This you may not be able to answer now. So what happens
buffer is full.
Yeah, exactly. Very good. Okay. So when you do a send, it does not. So there is way, you have seen the layers and everything. Okay. And then way below is your wire. Okay. And then it goes to the other side. Okay. So what happens is this when you send there, with every socket, there is a send buffer. We'll see how to get the value of this buffer out later on. Okay. You can see what is the receive buffer size and send buffer size of the socket. You can even change it, but then you need to learn a little bit more ways to make sense out of that change. Okay. But anyway, there is a buffer associated with it. Okay. So when you send and you saw that thing return, all it did was copy into this buffer. After that, all these other things will happen. The header will put on, then IP, then this, all those things that some we have discussed, some we have not, will happen before it goes out on the wire. So your send call returning does not mean that it has gone to the other side. It does just mean that it has been copied to the buffer. Okay, successfully. So now suppose for some reason, for whatever reason, it cannot send out anything, but you keep on doing sends. So eventually this buffer will fill up, and when the buffer fills up, okay, your send call, if you make it, it will block. So send is actually a blocking call. Even though right now you are hardly sending anything, you have a working network, so it's just going out to the other side. Stack is processing it and sending it to the other side. So usually you will almost never see send block in the settings that you're using it now, basically. Okay. Why usually I've never seen anybody get blocked in a send call here in IIT Kharagpur and so on, but it can theoretically block if you have in cases very few. So good to know that send is a blocking call. Okay, so having known that, we have seen. Just give me a second. Oh, I've written on the last slide. God knows why. Okay, anyway. Okay, having seen that, how can I make? So think about your receive. So you know that we have a problem that if I make a receive call, I will get blocked. Okay. Now I can block on more than one thing by making the select call, but then select is also a blocking call. So what if I want to do something like this? I would like to receive, but in case there is nothing to receive, I would like to go do something else and come back and try again later. So I don't want to get blocked, neither on the receive nor on the select or anything basically. So question is, how can we make the same thing applies for receive, receive from, send, send to all of them. Okay. So I'm just going to explain with receive. Non-blocking. So A, okay, so one particular receive call I want to make non-blocking, not all receive calls. Okay, we'll see how to do that also. So if you recall the receive, okay, the first three parameters, this was the socket ID, this was the buffer, this is the length of the buffer, and then you put a 0 out here for a flag. So far we have said that always put a 0 out there. Now here there are many different flags. I can put a flag. I'll show you code and run them right now. Just this. I can put a flag called message don't wait, which makes this particular receive call non-blocking. So if it does something in the receive buffer, it'll return you that just like a normal receive call. But there is nothing in the receive buffer. There is nothing has been sent, okay, or has not reached it yet. Then it won't block. It'll just come out. Okay. Is that clear? So all you have to do is to put this message don't wait so far. Okay. But there is a problem. If this is all I have to do, okay, there is a problem. Can somebody guess the problem? I'll give you a hint by putting this equal to here. What is the return value of receive? Anyone?
So when it returns 0, we won't know like whether the client is closed or it hasn't sent.
Exactly. Okay, good. So the return value of receive is the number of bytes that are actually received. Okay, this length that you put is the maximum number of bytes that you're willing to receive in this receive call. The return value gives what you actually receive. So for a blocking call, it should never return 0. Okay, but then there is this one specific case where it returns 0 if you're waiting on a blocking call and the other side closes the connection. So then the underlying system detects it. We'll do it in TCP later on. Okay, in theory, that this connection is closed, nothing is there in the connection, which means nothing can ever come. So in that case, return with 0. But then now, what do I make it return with? I cannot make it return with 0, but as somebody is very, as he said, returns with I cannot know whether the connection has been closed and therefore I should not come back and try to do receive again, or it's just that it's non-blocking. So right now there is nothing to receive, but something may come later on. Okay, so I cannot use 0. Obviously, I cannot use any positive value. So the only other value that is there is the negative value. Okay, so it returns a -1. Now, what is the problem? I don't know what is it an error? For example, I may have passed a socket, okay, which I have not created as an arbitrary value. Remember, a socket is just an integer value. I should have passed in a socket that is returned by a socket call, but I just somehow by mistake passed some other value. So then it will give me an error. Okay. So what happens is this. Remember when we discussed the error, okay? So there is this global variable called error number. It's a global, okay? And whenever you make a call, a system call, okay? In this case, the C library functions wrapping over the system calls, okay? If the call fails for some reason, this error number will be set to a specific value. P error is just a wrapper around that, reads that error number value and writes a nice message. For every error number, there is a message mapping in the file error number.h. So it just prints that corresponding value. But basically underneath, for every call, right after the thing, if you check the error number, if the call has failed, then the error number will be set to a specific value to indicate what is the failure. Okay. So the way we detect that there is nothing to receive now, but there may be something, is that if you use the message don't wait flag, this will return a -1. Okay. But then it will set error number to one of these two values, E would block or E again. So now you will write a code like this. You will say error equal to receive whatever your things, message don't wait. Okay. And then you say if error less than 0, that means there is an error, but then you will further check. Okay. That then you are checking if error number equal to E would block or error number equal to E again. Then you just know basically do whatever you want, temporarily no data. So now you can go do whatever you want to do and come back and check. If it's anything else, a true error. So then you exit and you have seen those codes out there basically. Okay, so that's how we will detect whether the receive call just temporarily there is no data, so I should come back and check it again. Okay. So let me do one more thing and then I will go and show you some code basically before we go to the next one. So this is fine if I want to make one receive call non-block, but then I have to write that piece of code for every receive call and so on. Okay, which is okay. We'll have to do that anyway because there can be normal errors also. But then what if I do not do this and I make every blocking call on a particular socket non-blocking, not just one receive or one send or something. Note that that means your accept call, connect calls and everything. Connect is also a blocking call because you may want to connect to the server, but the server may be very busy. Remember that listen parameter. Okay, so server may not accept your connection right now. Okay. So then you may actually, your connect call will also block, waiting for the connection. Now accept, as you have seen, can block it. So what if I try to make all these calls non-blocking, anything that can block on a socket non-blocking by setting something together, rather than having to specify that flag everywhere. Okay. So basically make all blocking calls non-blocking on a socket. So to do that, we use a function called FCNTL, file control. It's actually a generic OS function. Okay. So as the name suggests, file control, it allows you to control different aspects of how a file descriptor will behave, or the file pointed to by the file descriptor will behave. And in Linux, everything is a file. So socket, as we have discussed in class, okay, it's just one entry in your file descriptor table. So it's like a file descriptor, just that you make separate calls. Okay. So what FCNTL does, it has many different flags. Okay, so this is a bit value. Bit value is not a right term. So you may have 110101. Okay, so some 16 bits of this, and each of these bits means something. Okay, so this flag may mean, okay, whether it is read only or not. So if 1 is read only, 0 is not. So you want to set, make it read only, you will set this flag bit. Okay, so each of these bits means something. We'll just manipulate one of those bits out there. There's not too many bits that you can manipulate in Linux for sockets. Okay, or actually even for files, but there are quite a few still. Okay. So the idea is this. So FCNTL takes three parameters. One is this ID, which file descriptor you want to put in. So you put a socket. Then there is a command. Okay. And then there is an argument which is optional in the sense that it will depend on what this command is. Okay, I'll just show you one example. So what we do is this. I first want to, because this socket I may have set some other couple of other flags earlier. Okay, I first want to take out. So I think it is getFL. Okay, we'll see underscore or not. Okay, basically get flag, and then I pass it basically 0. What it does is basically whatever the current value of that flag, okay, that it gets you out into value. This argument is not necessary, so I just pass a 0 out there. Okay. So, but what does why do I want to get it out? I want to get it out because I want to manipulate only one bit in there, but the other bits I want to keep unchanged. So I don't know what the other bits that are already set, reset, and so on and so forth by earlier calls. So just get it out. I'll just bitwise or that one bit out there that I want to change. Okay. So now I will do, again, there's an error value that you can check. FCNTL, sockfd, setFL, and the flag that I want to set, I'll take val, I'll do a bitwise OR called O non-block. So these two lines of code basically leaves all other flags unchanged on the socket, but then every subsequent operation, okay, on this socket, if any of those operations normally are blocking, they will all become unblocked, non-blocking. Okay, so that includes receive, sends, accept, connect, anything that can block. Calls like listen and all are not affected because they are not blocking anything. Is that clear?
Yes, sir.
Okay. So these are just two ways you can make socket calls non-blocking. One way is to make all calls non-blocking together because you know that you don't want anything. None of them should be blocking. Other is that you want, maybe other receive calls don't matter, but this one receive call, you don't want it to be blocking. You want to say, oh, fine. I'll come back, check. If it's not there, no data, I'll go do something else. I'll come back and check again after some time. Okay. So let us go take a look at some code. And then we'll come back to do the other thing. Let me go to the, just give me one second. Okay. Oh. Can you see it or is blue bad? Can you see it? Yes, no, please.
Yes, sir.
Okay, good. Okay. So the first part of this thing is just normal. You open a socket, you bind and so on. So this is my client side. My server side is exactly the same. So I did not want to, I could have made server side also non-blocking. So accept can be non-blocking. You will do something, come back and try to accept again and so on. Okay. So this is an example, the first one that I will make only one receive call non-blocking. So my connect is still blocking. Okay. So I don't need to do anything for connect. So this is the piece of code out here. All right. So I put socket buffer is the buffer in which I want to do. 100 is the maximum number of bytes. I put a message, don't wait. Okay. And then I check the error number for you block or EOJ. Now you can do anything In this case, I'm doing nothing. I'm just printing no data, receive will block. I can actually do something and come back later. Let me sleep. So I just sleep for 1 second and I come back and check it. But this is the place where you could have gone and done some function call something else, whatever you want to do. Otherwise, if it is any of those other errors, then it's an actual error. Okay, and then you will exit as normal. All right. Then this normal thing. So basically, this is a call in which the server sends you something, just like the earlier. So what we will do is we'll make the server wait for 10 seconds before sending anything. So normally that means this receive call would have blocked for 10 seconds until the server sends something. Okay, but we will not do that. In this case, it will just come out and it print this message like 10, 11 times. Okay, and then it will actually read the message. So if I look at the server, just for completeness, it's exactly the same. You just see this line. Okay, so I have copied a message from server, but before I send it, I just made it send for sleep. But the connection is done. Okay. Okay. I just run the server. I've already compiled it. Server is waiting for the client connection. Nothing. And then I run. Okay. Just now see what happens. So every 1 second it is coming back and checking, but there is nothing. Okay. So it printed 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times. Okay. Because the server was waiting 10 seconds and it's coming back and checking every 1 second. Now this 10 second, 1 second thing is not that it has to be 10. Okay. The next assignment will give you an idea why. Okay. But then next time, after the 10 second, the server has woken up, server sends the message from server, and then this thing comes. So then this client sends a message from client, server is still waiting, client finishes. Is this clear? Yes, no, please.
Yes, sir.
Okay, good. What about the other one? This is a FCNTL thing. Okay. So here is the part where I have done this. So the FCNTL, the return values and everything is something. See, in this case, a val. Ideally, I should have checked the error value of val also. But normally, this all doesn't fail because it's just getting a thing. Okay, but it can fail if I've given it a wrong ID or something basically. So I normally should check for the error here also. Third parameter does not matter. It's just getting the flag out. And then it's a val underscore. So it's a f underscore get fl. Okay, so this I just said get fl. It's f underscore get fl. Okay, that's the name of the command. And then do val bitwise or with o non-block. So it only affects that one block. Okay. So now that basically I'm saying that everything on socket is blocking, your connect also, sorry, non-blocking, your connect can also become non-blocking. Okay. The connect code. Okay. So if I had not put this code, okay, what would have happened possibly is in the earlier case, if the server was busy handling other clients and cannot accept this client's connection, the client connection will block. Usually there is a timeout internally, don't worry about that. But initially it will block. Okay. But then in this case, what will happen if the server, unless I put additional code, because the connect has become non-blocking also, it will come back with an error. Okay. And unless I check that error to see, is it an error because the server is busy, or is an error that is a valid error because I set some parameter wrong or something else basically. Okay. So for a connect call, the error number value is set differently. It's not E would block or E again. It's called E in progress or E already. Actually, what happens the first time you make the connect call, if the server cannot accept it, it returns the error number that returns, not the server returns, the error number that is set on the client side is E in progress. Next time it's E already, meaning that it's already been checked once basically, sort of, okay. But these are the two things which basically are saying there is nothing wrong. It is just that the server is not responding to this connect request yet, but it has not sent any errors or anything, nothing like that. The connection has failed. So maybe if you wait some more time, it will happen. Okay. So I can say delay in making connection, let me sleep and retry after 1 second. Here you can go do something else and try to connect again later, basically. And I do this and then I come back in the while call and then I keep on doing. So every 1 second, if the connect gets actually cannot connect, it will come out immediately, and every 1 second I will come back and try again to connect. But the error codes are different. Okay, I'll send you all these codes and all. Okay, these are simple codes. And then I have my receipt. The same thing right there. Okay, I have to check the error code every case because I do not know it's a valid error or this just receive came out, because right now there is nothing to receive basically. All right, so rest of the code is the same. Okay, let's run this. Still running, so I don't have to do anything. Remember, it's now waiting at the accept call. The server, I'm still blocking server. Okay. So note this first line. Okay, there was a slight delay the first time it tried. Okay, your connect call actually came out with an error. Now you don't see it normally because normally it's a blocking call, so it'll just wait there. There was a slight delay. So the first time it actually came out with an error, but that error was in progress. If you check the actually print out the error, you will see. So it retried, then 1 second it slept, then it went back to connect again. Now it could connect. And now this 10-second thing here kicked off, basically. The accept call came back, and then the server was sleeping for 10 seconds. Okay. But you see one thing, see 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. These are not 10. Earlier it was 10. So this slight 9, 10 thing can happen for something that, you know, you should not exactly count this 10 second, 1 second or exactly 10, because it's not being checked exactly at that time basically. But the idea is that you will eventually get it. Is this clear? Everyone?
Yes, yes, sir.
Okay. So here's the another small thing, nothing related with blocking. But you see, you make all these calls. This is connect call here. Okay. Look at this thing. You remember what is the type of server EDR? Anyone remembers? This variable serve underscore ADDR. What is the type of that?
Socket.
No. Okay.
Socket.
Don't cut and my request is just a request. Don't cut and paste from sample code. Okay. Try writing everything yourself. To type you remember. Okay. This is not a very important thing to remember. But all I'm saying is that the calls sync in faster if you do that. So this, if you look up, it starts socket EDR in. Okay, is what internet address. Okay, but then you think that connect, bind, accept everywhere. Okay, I do this and then I do a struct socket EDR star. I typecast it to another type basically. Why do I do that? Why could not they have changed by now? Because everything in internet. Okay, could there be a struct socket EDR in already, the second parameter? So this basically says the connect call second parameter is actually of type struct socket EDR star. So if this parameter type was struct socket EDR underscore in, then I don't have to typecast it again and again every time I make those calls. Remember, you do this here, you do this in receive from, you do this in send to. Okay, all those places you do a struct socket EDR star. Every time you have to type this. Why? This is more a programming question. Okay. So if you go take a look at struct socket EDR star, okay, you will see it basically is a generic structure. It's something technique that we use a lot. Okay, so the first field is either an integer or an unsigned short. I forgot. Okay, but basically an integer. And then I think it's unsigned short, totally 16 bytes, 2 bytes unsigned short, most likely. Okay, and then the remaining 14 byte is just a byte array. There is no field like int, float, char, nothing you will see. Just a byte array. It is a very common technique for defining a structure generically when the structure can represent different types of things. So, as I told you earlier also, okay, even now we have a AF Unix and all we use and so on. So, there were many different types of networks. And then their address formats are different. So, either you may, if there are 4 types of network, 4 different variations of connect call. Okay, because in C programming, you have to give a specific type to the parameter. So it's a connect underscore in for internet type of site, connect underscore SNA for SNA networks and so on. Okay. Or you make a generic structure like that, and then you typecast the socket DR in which actually has those SYN-ADDR and all those fields out there, SYN family, SYN-ADDR, SDR, all those fields out there. And what your code will do, let's say the connect code, okay, it will first look at that first unsigned short, which is common for everybody, which is this SYN family field. Okay, so that will go into that unsigned short. That is common for everybody. If you look at that value, based on what that value is, it will interpret the remaining 14 bytes. So this value is this. Therefore, out of the 14 bytes, I have a 4 byte integer, 4 byte integer, and a 2 byte short. So this value is something else. I have a 2 byte short, 1 character, 4 byte integer, and so on. So I don't need basically separate versions of the calls for doing that basically. Okay, it's just an aside. But since I looked at this thing, I thought I will mention this. Okay, so let's go back. Oh, I discarded anyway. Should not have discarded anyway. All right. So that's about non-blocking calls. The receive flag, there are 2 other flags that you will see that are of interesting, not too often used. This is called a message peak and message wait all. Okay. So message peak basically says what the name says. It allows you to peek into the receive buffer and not do anything else. So it'll behave as a normal receive call. You'll still get the number of bytes in the buffer and so on. It'll give you those bytes and so on, but it won't delete the things from the buffer. So the next time you do, so you can do some things like this one problem that something, you want 10 bytes to come before you do something. Okay, so you can peek into it and you can see what, not just 10 bytes, but some specific 10 bytes. Okay, so you can just find those 10 bytes and then see, oh, this has not come, then I will not do something. But this does not affect the data because you can read it up later. Not very highly useful in my opinion, but you can do that. And this is the other one, but this is a tricky one. Okay, which says that, remember the receive call. Okay, you had this third field which says what is the number that you want. You can specify, let's say 16 out here. This is buffer lane. Okay, and this message wait on flag, if I put here, it'll wait for 16 bytes before it comes out. So it don't wait for 12, it won't come out in 12 bytes or 11 bytes or something. So apparently, based on your first, third assignment and so on, some people may find it useful that I want an integer, I want to wait for all 4 bytes to come together. Okay. But use this with caution because there are other things that can happen. Okay. As you ask me, like end of the course, I'll explain. You need some OS concepts for that, signals and all. Other things that can happen that can make it come out even when there is not 16 out there. Okay. So you'll have to check for the receive thing, the return value again and again. So. But these are another 2 flags that you can think of. The O non-block is used a lot. That's the interesting fact. Okay, any other questions on sockets before I move on to the next topic? That's something that we'll need for the next assignment. All right. In that case, the next thing that we do is more an OS thing, something called thread. So in your OS, I think you have not done pthreads yet, right? It's not usually not so soon. Have you done it? Anything called pthreads?
Yes, sir, we were.
You did pthreads? Great.
Yes, sir. In
Okay.
theory class, we were taught, sir. We did not do anything.
You didn't do anything. Okay, good. So that saves me some trouble. Okay. So basically, the next assignment will give an idea about doing something inside the stack, but it's not going to be inside the stack because we don't want to muck up your Linux internals. So we'll do it on the user level only, write programs and all, but we'll give you a flavor of how this, some of the things that you have done gets done inside this. And we'll see that unlike the application codes that you have read so far, or done so far, basically, the stack cannot be sequential. One thread cannot do everything. Okay. If you are waiting to receive something and something else needs to happen, who is going to send the one? Okay. So at least you need 2 threads. Okay. You actually need more, as maybe once I do things at the very end, I will talk a little bit more about. But you need more than one. So we have to give flavor of that. So and the concurrent servers that we have done, we have used fork because we did it at the very beginning. Fork is easier to teach. Okay. But even if you think about web servers and all, what gets created for a concurrent server is actually a thread. Okay? So there will be one thread for every request and so on. Okay. So what is the difference? You have done pthreads. Okay. Thread and a process. Do you know anyone? There are lots of differences, but what is one of the main differences? Yeah.
We shared memory, sir.
Exactly. Very good. Very good. Okay. That's the one that we'll need. Remember when we did fork, okay? So think of this. Suppose we'll make it simple. We have a global variable index equal to 5. When we did fork, okay, both these processes got a copy of this variable. So if I change it in one, the other does not get affected. So now, if I want to make these 2 processes communicate, I have to create something that is shared by both in the middle explicitly to do this. And in OS, you will see there are things called shared memory, message queues, and so on. Okay. But then in thread, one of the big differences is threads share the memory. There is a way to make local thread variables also that is local to thread. But in general, we'll stick with the global variables, with the simplest kind of variables you can think of. If I now create a thread using pthread create, okay, each of those threads will have the same copy of X. That means if somebody modifies to 6, all the other threads will see that 6 out there. So that's the main difference, and that's the difference that we like to keep. Okay, so what we need to do to create a thread, make the thread do what we want. Okay, and we need to do something called mutual exclusion, and then destroy the thread. Again, if the process goes out, the threads are destroyed explicitly, but there's a call for destroying the thread. So, creating the thread, we do call called pthread create. So, when did you do your pthreads? Like last week, this week? This week is Monday, so I don't think so. So have you done the pthread create call? Yes, no. Understood, done. Okay. No issues. Let's do this. Last class. But then you were busy with the old USSN, right? So should I do pthread create? Yes or no?
Yes, sir.
Yes, good. Take it. So basically, these two things are together done with the pthread create call. Then we'll do this mutual exclusion. We'll do the destroy thread is simple. Okay. So what does the pthread create call do? So first of all, every thread has an ID. Okay. So it gives ask for a place to return the thread ID. Okay. Parameter here, I'll always put it 0 for now. Okay. You don't need to know. Okay. Then this thing is what function should this thread call? Okay, on start. When I first create the thread, it calls some function automatically. Okay, and this function has to be of a special type. Void star, name of the function, void star. No other type of functions can be allowed. Okay, but we'll see that's not really any kind of a restriction, basically. And finally, arguments to pass to the function. I write arguments, why we'll see, but because it takes only one void star, so this will be a void star. Okay, this type I will not write it. You should see the man page and try to make sense out of it. Okay, how do I specify? Basically, whenever function has a parameter, which will be new to some of them, I specify a pointer to the function. Okay, but then I have to specify what type of function. So this becomes a little bit complicated. But the call is very simple. Okay, and this one is actually a specific type called pthread underscore t star. Okay, it's basically a long int. Okay, but then it has a specific name pthread t. So I pass a point just like an integer. I pass a int star to return the value. For a returning the thread ID, I pass a pthread t star. Okay, so that's my pthread t call function. Right? We'll look at code basically to do this. So basically, what will happen is I will make a call like this. So I will declare, let's say, pthread underscore t, let's say thread ID. Let's suppose I will create 2 threads, just suppose. So one for each thread. Okay, and then I have a function, let's say, called void star print void star s. Okay, and suppose it's just send me a string message and I'll just print that. Okay, so what I will do is it's a void star. So I'll first typecast this. So this is a cat star p, sorry. Okay, do this, and then I say printf %s p. All right. So this is what I want the thread to do basically. I just wanted to send me a when I create through the argument, send me a message, and then I will just print this thing. So then I will make a call called pthread create underscore. Okay. So thread ID 0 and thread ID 1 and pass in different ways. So let's say I say thread ID 0. So first thread's ID will be stored in here. This is 0 always. I just have to pass the name of the function. Okay, print, and then I have to pass a message basically. So I can do it in different ways. Suppose I've stored the message in some buffer or something. So I can just say buff. Okay, or you can just directly give a string also with a quote mark and so on. You'll take whatever is in the buff. Okay, null terminated. We'll pass it there. So the effect of this is to create a thread, store the ID of the thread in the variable thread ID 0. I can print it out. Okay, automatically call the function print, passing this as a void star parameter, and then it's up to you to do what you want to do with it inside. Is this clear?
Yes.
Okay. Now, so I've done this create a thread and make a thread. Okay. What about this mutual exclusion thing? Okay. Now I've created two threads, right? I've created one thread. You can make another call with the thread ID, thread ID 1 and so on, storing it in the thread. Okay. So now suppose in that function or the function, some other function that is called from that startup function and so on, I have a variable. This is what we will do in your code also. We initialize to 0. So all I want to do is this. Now I have two threads, T1 and T2. Okay. I want in that T1, in the startup function, to do count plus plus. It's a global variable, so it's accessible to all functions, not a problem. I don't have to pass as parameter, and a count plus plus. So this is my global. Okay. So both those, instead of print, I have a count function or something, and do count plus plus in the function that is called by the thread. Okay. What is the value that I expect after, if I print the value after the two threads are over, what is the value that I expect? Stupid question, but human. Hooray, yes, there's no trick question yet. What do you expect if you do 2 count plus plus after 0?
2.
2, right? Okay. Now, depending on something underneath, okay, it can be either 2 or 1. Okay. Now, what is the problem? Okay. You are writing in high level language count plus plus. You have gone through an architecture course and you know this count plus plus can be implemented by machine language in different ways. So this is a standard example in every textbook and everything. Okay. What will happen? So this is count is what? This somewhere in memory. This count variable is stored. Okay. Now, suppose in an architecture, there is no direct memory increment operation. Okay. So then you will load this memory into a register. You will do an increment R and you will store R into back to the n. Okay. This is what T1 is doing. T2 is doing exactly the same thing also. Okay. Now, if T1 does everything, all right, and then T2 does everything, or if T2 does everything, then T1 does everything, okay, then there is no problem. Okay, but here is a possibility. Why this is a possibility? We'll see. So let me prepend this by 1 and by 2 to indicate that this is the 2's load storage something. So here is a possibility. Load RM, the second load RM, okay, 1 increment R, 2 increment R is one of the possibilities. Okay, 1 store RM, 2 store RM. Now what will happen? One will get, both of them actually get 0 because when this is loaded, this change is not affected in M here. So both of them does 1. So these things both write 1. Writes 1, writes 1. Right? Do you agree?
Yes. Yes.
So my final answer is 1. But how can this happen? Suppose I have only one CPU, one core. Can this happen? This is something you may not know yet, but at least you should know the yes, no for now, at least from based on architecture knowledge. What do you think?
Yes, it cannot happen.
Why cannot it happen?
If there is only one CPU, then
Yeah. So
two processes.
you're right.
can't
You are
run
right. Just
parallel.
finish your answer.
It can't run parallel to instructions.
Right. So whoever has got the CPU will do all these things. Only when it ends, the other one will get it. Right?
Yes, sir.
But here is a problem. Okay. See, ever wonder on a Linux machine, okay, a Windows machine, you have 5 different windows. Okay. and do this code basically. You do a while one, printf a, the character A. Okay, and you write 5 different variations of that, printf a, printf b, printf c, d, e, 5 programs, and run them on 5 different windows. By your logic, only one of them should have got printed if there is one core. Even if there are 4 cores, if I write 6 of them, 4 of them should get printed. But you will see each of those windows printing something. Because this is something you will learn in the OS scheduling next. Okay, because your systems are typically time shared. So each of those things running will not run indefinitely. You get a quantum of time, maximum 100 milliseconds. At the end of 100 milliseconds, it will give up temporarily, get stored somewhere, and another one will run. Then at the end of 100 milliseconds for that will also get temporarily, and see this kind of one possibly round robin that this will happen in round robin fashion. So 1, 2, 3, 4, 5, then 1, 2, 3, 4, 5 again, then 1, 2, 3, 5 gets. So everybody gets some chunk of the CPU over a period of time. Nobody is starved out. Okay, why we do that is a different thing that you will learn in this. Okay, but that's the reality in modern day machines basically. So it is highly possible, okay, for other reasons. Okay, this is a toy example that your T1 got, okay, CPU taken away from it after this, T2 got it after this. Okay, or even if T1 gets after this and T2 runs again, okay, note that even this one is load RM. If the CPU gets taken away from it and 2 gets to run, even if 2 finishes, the damage is already done. So 2 does this, 2 does increment R, okay, 2 does store RM. So here you write actually 1, and then 2 is done, 1 starts running again, increment store. But then it's increment on what it has read earlier, which is 0. So again it will write 1. Okay, so because of this business of time sharing things, you can actually have one program not finishing completely and gives up the CPU temporarily, and something else runs. Okay, so I cannot do that. So I have to stop that either this thing runs completely or it does not run at all, or at least in the middle of this cannot run. Other things may run. I cannot stop the OS scheduling just because I'm writing a flexible program. But OS should give me some way of saying that these 2 programs should not be interlinked. Are you with me? Yes, no?
Yes, sir.
Okay. So what I'm saying is this increment or this code, okay, and this code, this is what we call a critical section, should be mutually exclusive. That means when one is executing something on this R, this is a shared variable, sorry, count, rather not this code and this code, it's okay, same thing. This code and this code, this is just translation of this code. But let's talk at the higher layer. On your program that you write, you say, I want to do this to mutually exclusive. So if this runs, this should not be able to run. This can run only after this finishes. It cannot sneak in the middle of that by things like this. So this is what is the classic mutual exclusion problem. Extremely important problem, okay, as you will learn in your OS, and very hard to debug if you do not do it properly. So we'll give you a very simple scheme for doing this because you will have to do this. So this is where, okay, pthreads gives something called a mutex. So define it like this, okay. Say call it mutex1. All right. And anywhere this thing happens, there's the initial call, we'll show you. Pthread mutex init. You have to first initialize it. Okay. And mutex1, I think this parameter you can keep now. Okay. And then wherever you have things like this, things that you do not want 2 threads to concurrently access, you put this, just encapsulate this in this pthread mutex lock. You kind of lock this space, okay? Ampersand mutex1 and then pthread mutex unlock ampersand mutex1. So just think about each of those variables which are shared between threads. So more than one thread can write it. Reading is never a problem. If all of them read it, there is no problem. But you think about the ones where more than one thread can write it. Okay. Anytime you see a news like this, okay, you put a pthread mutex lock before it and unlock before it. Declare one mutex, initialize it, and put this. So this, the OS guarantees you, do not worry how you will learn in OS, okay, that if somebody has been able to access, kind of go past this thing, it's kind of just locked this part. So until it executes this statement and unlocks it, everybody else trying to execute a mutex lock will get blocked out here. So if this is T1, then T2 is doing the same code. Okay. And mutex1 will declare as a global, so both of them have access to the same mutex1. But then if T1 has been able to go past this, it has kind of, you have just kind of gone into the room and kind of locked it from inside. So unless you unlock it, everybody coming to the door has to wait at the door. So the other process will get blocked at the pthread mutex lock call. When this does unlock, it will again be able to go. And then it will do the count plus plus. This guarantees that this count plus plus is done, or any write operation on a shared variable is done on by only one thread at a time. We will see similar calls for processes and so on. Okay, and this is something that we use, the extremely important, omnipresent thing in multi-threaded programming, multi-process, multi-threaded programming. We'll learn more about it. It's not, but this will suffice for us for now. Okay, there are lots of performance issues and so on. But so what you need to know for the next assignment is a pthread create call. Okay, how to define this mutex lock and unlock. And there's a pthread destroy and mutex destroy call, mutex init and all those things. Again, we'll show you code. I will give you that code also. It's there earlier now. Yes, it's been taught. I'm sure mutex may not have come. Okay, so that when we discuss the assignment next week, it will become easier for you. So I understand you are busy, but this week try kind of running this course a little bit. A very small course. So you could say that. Is that fine? Before I go to the code, are there any questions? No? Good. Always ask us later also. So let me go to the okay. Okay. You can see the file, right? Yes, no?
Yes, sir.
Yes.
Okay. So there is again this implement. So this one is just data structure I have defined. There's nothing standard or something. Okay, but I defined it for a reason. You see, it's a very strange data structure with only one field. Okay, I might have used an array of, even if I wanted multiple of this, I could have used an array of ints and so on. But there's a reason why I do this. Okay, this roundabout thing of having just one integer encapsulated in a structure. So this is what I will do in this program. Okay, I will create 5 threads. Each of them will update a global thing, global count. Okay, and then exit. That's all it will do. Right, and then at the end I will print the count. It should always print 5. Okay. So this one, all I'm going to do is I'll come back to this main program. If you look at this struct thread data, param num threads. Okay, I have basically just going to keep for thread 0. The first thread I will put a 0 in there. Okay, so param 0 will be 0, param 1 will be 1, param 2 will be 2, and so on in that int field out there. This kind of saying thread 0, thread 1, thread 2, thread 3, thread 4. Okay, this is because the thread ID that gets returned, you will see is a long big number. This is a long integer. I just want a very simple way of saying this is my thread 0, this is my thread 1, thread 2, and so on and so forth. Okay, that's all I'm doing. Okay. Now in the globals, what else have I done? I have defined this pthread T structure, the thread ID, num threads, so 5 threads. Remember that this is the one that I'm going to use to for pthread create to return the corresponding thread ID. Okay, and I've declared a pthread mutex to mutex one. So they're all globals. Okay, that means any thread that I create will be able to access them. And this is shared copy between all the threads. So they're accessing the same variable. Okay. Okay. Come back to this void thread start. So what do? I do start thread data this pthread mutex init. Okay. I initialize the mutex. And then for 5 threads, I do this, as I said, param i.tindex, that one integer structure field. In one integer field structure, I put the thread ID basically. So param 0.tindex will be 0, param 1.3index will be 1. It's just something that I give the threads basically, thread ID basically, not the system return thread ID. Then I create the pthread create the thread using pthread create. So param 0.tindex is 0. And then I call the thing. I store the ID that is returned by the system, the pthread create call, into thread ID 0. Okay. Second parameter is null. They will all execute the function thread underscore start. And the parameter, remember, I can pass a single void star parameter that I'm passing is nothing but the pointer to that parameter. So basically, I want to pass that, this one 0, 1, 2, 3, 4. Those are the ones that I want to pass as parameter. But I have to pass as void star, not as an int. So I pass a void star typecasting of wherever it is stored, the ampersand parameter. So ampersand param 0, I will do a star out there, so I'll get back the 0 out there. Right? Okay. So, okay, I'll come back to the, okay, let's do the thread start. So then first time what happens, param 0.tindex is 0. We'll store the thing in thread ID 0 and call thread start. Moment it finishes with that pthread create, remember now I have 2 things. My original process going back to this for loop and the first thread that is created. What order they will run is completely up to the scheduler. You don't have any control over that. Okay. But this other thread has already started executing this start thing if it is scheduled. Okay. So now let's look at the thread start function. Remember, it's actually a void star and with void star thing. Okay. So I just get out the integer out of it. So void thread data start t param. So anything that is passed at a void star is a parameter. I can just appropriately typecast it. In this case, it is struct thread data start. Okay. So that I store in a same type variable, and then that star.tindex gives me that thing. So that 0, 1, 2, 3, 4 comes out. Are you with me?
Yes.
Yes, no? Yes, no, please. Should I repeat?
Yes, sir.
Okay. This simple parameter, just an integer parameter thing coming out. But I have to pass it in void star, so I did this roundabout thing out there. Then I want to do global count plus plus. But then while I'm doing this, main is not sitting idle necessarily. So main may get scheduled, may create the next thread. That will also start executing the same thread start function, but with a different parameter value. Okay. So this may also come in, thread 1 may also come in and start doing this global count plus plus and so on. So I don't want more than one thread to do this global count plus plus. So I put it in mutex log, done this mutex unlog. So if thread 0, thread 1 and thread 2 all try to do this together for some reason, only one of them will be able to go in. This is, as I said, like going into a room, locking it from inside. While that is doing global count plus plus, all of the others are waiting at the door, which is this lock statement. When this finishes and unlocks, then only one of them will be able to go in. 2 of them cannot rush in. How that happens, that is enforced by the OS. You don't have to know now. You will learn in your OS course. Okay. So after it does done that, it is just going to say thread. So this is the one that is printing is the original thread ID returned by the thing. So we'll see the output. And then there is a function called pthread exit. Actually, if your start function finishes, it will automatically exit, but you can put a explicit pthread exit also. All right. So every function, every thread. So this loop creates 5 threads. Each of them executes this function. But then this first one passes and param 0, next one passes and param 1, next one passes and param 2, and so on. So this TID that gets, the first one will get 0, second one will get 1, third one will get 2, and all. Because that's what I put in here actually in the icon. Just, you don't need to know this call. I put in if you want. So you can actually make all of them wait basically until everyone has finished. It's something we may not need in the next call, but I thought I will put this nice piece of thing. Okay. So next both parts actually are not reading yet. Okay. Well, this print is needed. So okay, anyway, let me do it. So pthread join thread ID thing basically says that wait till one terminates, kind of. So the pthread join call will block basically at this thread ID basically. So the effect of this piece of code is basically to join all the 5 threads. Basically, when all of them are finished up to this point, okay, not terminates, wait for all threads to not terminate in the sense the thread gets over, but finish up to this point, then only each thread will go up there. This kind of intermediate synchronized point to say no thread should go further than this until all threads have finished up to this. Okay, so that is what it boils down to basically. Okay. Actually, no. Sorry. This one will basically, so this is one thread, sorry, this is the main function. I'm sorry, this was wrong. This will actually wait for the test to terminate. So this is the main function. Sorry. Okay. That was another call. So this call made here will do this. Okay. So look at the thing. This is the main function that is doing this, not one of those threads. The threads are in that thread start thing, and they will exit after they do this. Okay. So each thread will terminate here. What this main function is doing, okay, is basically waiting for pthread. When it makes the first call, it is waiting for thread ID 0 to terminate. So when the main function makes this pthread join call, it will get blocked here until thread ID 0 has terminated. Now when thread ID 0 gets terminated, it comes out of that block, goes for I equal to 1. So the thread ID 1, whatever the thread ID is there. So effect of making these 5 calls, I'm sorry I was wrong earlier, that's a separate call, is for the main function. So there are 6 things basically, the main function, the main process, and 5 threads created. So this is for the main process to wait for all the 5 threads to terminate. Okay? Which means when you are here, you are aware, you are sure that no other threads are running. None of those 5 threads are running. Okay. So then you could have directly just printed the final count, but read the comment out here. So for this particular code, this mutex lock, mutex unlock here again is unnecessary because there is no other thread. All of the other threads are terminated. But I just wanted to highlight this because, in a real program, there will be other threads running and so on and so forth. So it's always safe to do this if you're not sure which other threads are running. Okay. So I put a comment out there. That is just for good practice. And then finally, you should always destroy the thread. Again, if the process goes out, in this case, the thread will be automatically destroyed. But again, you may be writing large programs where you create thread destroy, but the main process keeps on running for other things. I'll run it, but before that, is there any question? So sorry for that confusion on pthread chart. Okay, if not, my old server is still running. It's already compiled, but I want to show you something. So when you use pthreads, you have to do that pthread.h include. And you have to link with the pthread library, which is libpthread.a or .a. So this thing. So just like -lm, you do -l pthread. Okay. And now if I run this thing, you see these are the 5 threads created. Okay. And this print is coming from that print startup function that you have out here. This is the place that is printing this. Each of them have done this. Okay. I could have printed the TID also. Let's do this. Why not? Just give me 1 second. I think it's simple, but still, let's do this. Thread 0, 1, 2, 3, 4, the TID thing that I passed in here. Each of them are getting a different parameter, of course. And this is the actual thread returned by the pthread create call. They all finished updating. So only after that did the main function finish this thing. So you can see that this final count will not appear from the main until all the threads terminate by doing this simple thing. So let them print. After I have done this, let them sleep for 2 seconds. Each of them sleep for 5 seconds. You will see this final count is 5 will not appear until all these 5 things are done, even though main does not have any sleep. Which is in the 5-second sleep. But main have created all 5 of them. So this 5 comes very together because main does not have any sleep. He is going in that for loop creating the 5 things, but each of them waits after increase. Okay. But this will come only after all 5 of them finish. This will not come first. Okay. So that's, I think, all. There's one question I wanted to ask you. Yeah. So is this clear? Use of these calls?
Yes.
Okay. So why did I do this? Any clue? I could have just passed declare an array of 5 integers, and instead of doing this and this star void star, this is void star and ampersand that thing. So I did this to just show you something. Okay, it's more OS thing than anything. That see the structure of that function that you call, the prototype of that function is fixed. You cannot call an arbitrary function. It has to be void star and with parameter void star. Okay. So now one parameter, you just want to pass an int, you could have just done a void star ampersand that int value. Okay. But then if it takes only one parameter, void star, one void star, and you have to pass more than one parameter. You have to pass 3 parameters, so 4 parameters for your need. What do? Basically, you package it into a structure and pass a pointer to that structure. Because the function knows what is coming. You are writing that code. So it just typecast it to the appropriate structure and take out the fields. So you want to pass 4 parameters, you will declare a structure like this, set all those parameters in the structure fields, and pass a pointer to that one structure. Which is what I did, but this is trivial. I could have just because I just want to pass one parameter. Okay. All right. So we had around 1 hour 15 minutes of class. So that's all I have to say today. Assignment going okay for everyone? So these codes I will just, because there are 2 sections and we posted different places and so on. I'll just send you by mail all these 3 codes. Basically. So very small files anyway. Okay, so that's all I have to say. If you have any questions, let me know. Otherwise, class is over and then you can leave. Let me stop the recording.